Hello, everybody. This video is for a course Maths2099 at UNSW. This is the question 48 that I'm going to solve. It's about the projections of a vector on a vector space, W, and its orthogonal complement W, perp. So assume I just would like to give a formula in the beginning. You know this one from your lectures, but just let's remind ourselves how to solve this problem. Assume we have a basis B1, B2, Bm. If it is an orthonormal basis of W, it means that Bi, Bj is equal to 0. This is a dot product. If you take any two vectors as a dot product, and then it will be 0 if they are different vectors. If you multiply dot product to itself, then you will obtain 1. Such a basis is called orthonormal basis of W. And we would like to find out the projection of a vector, any vector, on W. This is defined as then you're taking X and multiplying all B1, B2, Bn as a dot product. And these are the coefficients of the linear combinations of B1, B2, Bm, right? So these are the vectors B1, B2, Bm, and we know that every vector in W can be written as a linear combinations of those ones because it's a basis. And even more because these vectors have units 1. And the coefficients of those units are obtained with the dot product with X. So this is by definition, we call this vector is the projection of the vector X on the vector space W. As you realize that this is the definition, this definition works for only the orthonormal basis. If any basis is given to you, you need to turn that orthonormal basis, turn that basis to an orthonormal basis. And we know how to do that. We practiced that last week, right? So this is the formula for the projections of the any X on W. And these are the coefficients. You obtain these coefficients by just multiplying each basis vectors with the dot products of the vector that you're working on. And these will give you the coefficients of basis elements. And the projection of this of X on the orthogonal complement of W, which is W perp, is given by this definition. You just take the X, and then you multiply, you just take the X and take away projection of WX. So that's the definition of it. So this vector is perpendicular to W, so it is in W perp. For another way of doing this in a matrix form, if you construct a matrix B with B1, B2, Bm, and you multiply this matrix with its transpose, and then the matrix that you're getting here will correspond to the projection of W. Projection of W is equal to QQ transform. This is the matrix form of the projection of W operation, because this operation acting on the vector X takes the X to the vector, the projection vector of X on that vector space. So this is the matrix form for this procedure. Then the orthogonal complement is just a subtraction. Let's do the example. It's question 48. So W is given by the spanning set of these two vectors. And we know that every spanning set is a subspace, which is just because of the definition of the spanning set is the linear combinations of the vectors, which will give you a subspace. And the question is, find the projection of X onto W. We would like the projection of X with the same vector onto the orthogonal complement of W per. Okay, the solution, W1 and W2. I call this one is W1, this one is W2. First is we would like to check whether is this an orthonormal basis, because we have a formula if it is an orthonormal basis. So we need to look at the dot products of these vectors. Dot product of W1, W2, W1, 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 W2. So I would like to look at this dot product and construct the multiplication table. That's the easiest way to do it, right? And when we multiply W1, W2, we get a constant term. And if we multiply W2, W2, we have a constant term. It means that this set, W1, W2, is an orthogonal. It means that only thing that we are missing is that the length is not right. So if we divide each vector by its length, which is the square root of the dot product by itself, which will give us 1/3. So 1/3 W1 and 1/3 W2 will be an orthonormal basis. Then we can work with that one. The definition says the projection of this X vector on W is the X times to the vector, orthonormal basis vector itself. This is a dot product, so this will give us a real number. And this is a vector, and this is the first basis vector, orthonormal basis vector. And X and a dot product of the second orthonormal basis vector. So this will give us the real number, and that is a vector. Only thing that we need to do, just figure out these coefficients, basically. But I need a bracket here. So let's figure out these dot products. So this was the X vector, and this is V1 for us. If 2 times 2, 18, and minus 8 will give us 12. And we have 2, 9, minus 4. This is X, and this is 2, 1 minus 2. That's W2. Dot product of these two. I have a dot here that is missing. And this will be 4, 9, minus will be plus 8. That will give us 21. So this number here, 12, and this number is 21. So, but we have 1/9 in the beginning. And then we have 12/9 W1, 21/9 W2. So we have this, if we simplify this one, that will be 4/3. And if we simplify this one, we will have 7/3. And W1 is 1, 2, 2, and W2 is 2, 1 minus 3. And then we add these two, we will be able to get this vector multiplied by 1/3, we will get this vector 6, 5 minus 3. So that is the projected vector of X on W. So this vector is in W, is in the vector space W. Okay, now we could do this with the constructing the matrix. So the Q matrix will be the 1/3 W1, 1/3 W2. These are this vector and these vectors give us the orthonormal basis. And this is 1/3 of 1, 2, 2 to 1 minus 1. If you take this transpose and multiply it to itself, so 1/3 from itself, 1/3 from the transposition, sorry. So we have 1/9 in the beginning. That is Q, and the transpose of this will be, this row will be this column will be the row, and this column will be this row. And then we multiply these two matrix, we will have this matrix, and 1/9 stays there, of course. So we will have this matrix. This matrix corresponds to projection of W. This is like an operation. We are thinking of this one like an operation. And asking us the question that what is the projection of this vector on V is basically you multiply this matrix and the vector will get the result. So this is another way to calculate the same vector as we calculated here with the matrix way. I'm using a matrix multiplication here, matrix representation for the projection here, and I'm getting the same results. So this is another way to find out this. Okay, but this seems to me an easier option if as fewer steps. But this is if you have more than one X vector, so this is the best way to go. But if you have a one vector, this might be the much more simpler way to do the calculations, but it's up to you. Both of them are fine. Only thing, the projection of the same vector onto the orthogonal complement of W perp, will be just a subtraction. We subtract X minus projection of the WX. So this is the X vector. This is what we found. Subtraction will give us this vector. That is the projection of X on the vector space, or that the vector space orthogonal complement of W. We call W perp. Okay, so that's it for this question. I hope it is useful for you, and thank you very much for listening.